So, can we start again, please? Okay, let's look at the next. Let's look at the last set of improvements that one can make to the algorithm, and this is basically the one thing. I think the first one is the one that made the biggest difference in algorithmic terms. The idea is basically that if you find a clause in your clause set for which you only have one literal in the clause set. So suppose you have a clause set A, and then you have not A or B, A or not C, whatever. What does it tell us about A? A must be true, exactly. Yeah? So this clause set can only be satisfied if A is true. And this is now, maybe I should have written it down to make it more clear. This would be something similar. It still is A must be true. Or if I had a B here, what would it say over B? B has to be false. Yeah? Hmm?
If it's not B, assume this model, there would be no model for this.
Exactly. Yeah. If in whatever assignment we have for these three variables, this one can only be satisfied under the condition that B is interpreted to be false and A is to be interpreted to be true. So we can always start with the unit clauses, as they are called. So the unit clauses are the ones where you have one literal only in a clause. So that's basically, if you have a unit clause, choose this one to branch. That's improvement number one. And the other one is, suppose that you have a variable that occurs only positive, so without a negation, or negative, so with a negation. It doesn't matter what you choose. So the alternative to branch on the if a literal does not appear negated, that's a better way of explaining it as written here. If it doesn't appear negated in the formula, then we can always set this literal to be true. And that's called the pure literals. So let's see how this works out in the example. Oh, first the code, sorry. So basically it's the same as we had before, but then we now add if my clause set contains a unit or a pure literal, then branch on this literal first. And after that, if you don't have one of those, you can still branch in an informed way or in a random way, whatever. But always start your recursion with the unit clause. So now, this is basically what the Davis-Putnam algorithm does for real. You start out with your clause normal form, your clauses. Again, you start with a variable because we don't have any pure or unit clauses. You make the assumption that A is false. That's the usual start we did before. But now we come to the situation where we have a unit clause. So basically we can now choose B or C, it doesn't matter in this case. But what we know is that we have to choose B to be false. Yeah? So we've done that, nothing changes. I think this one should also go, to be honest. I think there's a mistake in the presentation here. So this one can also be deleted. Oh, it does. Here it goes. So once we decide on B to be false, this one goes. And then we have two unit clauses we delete, and we've done this branch. So now the other direction is the one where, and because we have done this now, we don't have to do the backtracking. We can go to the A immediately. Now we choose the A to be true, and basically we have a unit clause here, and we find the solution immediately. So this unit clause, application of the unit clauses, helps us immediately to branch the entire middle of the tree. So these are the strategies that you have to learn. It helps you in a complete and sound way to prune the tree. So in a way, it's a very similar idea to alphabetic pruning, because you know that you only have to consider the part of the trees that don't have impact on your decision of satisfiability or not. So in reality, in the example that we had now, we started with A. And the choice of starting with A is simply because it's the first letter in the alphabet. There was no other reason of starting with A. In real life, you have more information about clauses, about literals. Some of them are more relevant, maybe the chance is higher that you find a contradiction, chances higher that you find a model also. And this is basically what we've seen in the first week, where you would use heuristics for. So which of the symbols, the literals, should you start guessing your value for? So what is now the place to put in a heuristic value? Of course, we have this choose P and F. And here is where we can choose in an intelligent way. So in principle, this was, up to now, was a simple unordered, what was it? Queue or stack? Stack, I guess. But now it would obviously make more sense if we would use a best first search. Yeah? And best first search would, in this case, give us a heuristic which says the chances of finding a model or the chances of finding a closure is higher than by choosing another symbol. And there are surprisingly simple heuristics that really help us close the search space almost immediately. And in a way, you want the variable that has that is most easily finding a contradiction, because if you choose on not so relevant variables, you might end up at a choice of a variable which is involved in a contradiction. And that basically means that there are many constraints in which it plays a role. And if you start choosing the wrong one, you will have to redo this closure again and again and again and again, every time you do the backtracking. So if you start with the constrained ones where your chances are high that there is a contradiction, your chances of sort of cutting off big parts of the tree are highest. So you're looking for heuristics that, in the case that we don't have unit clauses, if we have a unit clause, we always apply it. Unit clause is the first thing to apply. If you don't have a unit clause, you basically decide on the variable that's the most constrained, so that's involved in most of the clauses in your data set. And if you have a very long clause, then the chances that it plays a role is also smaller. So basically, one of the most powerful heuristics that people have applied is the MOMS heuristics, which says the most occurrences in clauses of minimal length. You've all built your heuristics in the first week, so you see that this one is one that we can easily calculate, easily work with. So that's a good heuristics to help us choose the right variable to give a partial assignment to. And there are many more, so it's an information theoretic problem to choose the right one to help us do this decision problem. But this one is one that you should know because it's so easy and works really good in practice. So Davis-Putnam was a procedure that was invented in the 60s of the last century. In the beginning, they had very small base, but there's really very extensive work on satisfiability, SAT solving. And in the 90s, they got up to hundreds of propositions. Nowadays, the modern ones, they really manage to have up to 1 million of propositions. And remember, if when I talked in the beginning about the naive way of doing the search through the truth tables, that the complexity of the problem is 2 to the power of the number of propositions. So if you would do this naively, this would simply never, 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 ever work. So this is the power of these sort of generic reasoning algorithms, that they have been so optimized that you can deal now with problems that are really complex. And I think that our example, if we have a really complex model for a Schnapsen game, we might end up with a problem around the 1,000 propositions. That might be too much, but still. And I have bad news for you. The SAT solver that we have provided was written by Peter. It applies Davis-Putnam. Unfortunately, I don't think it applies many heuristics, so it will probably die with these numbers so it will be not that efficient. But the good news is that if you really run such a big knowledge-based reasoning algorithm, there are tools around that you can easily integrate in your implementation of the knowledge bot, and then you can really sort of get loose as you want, because nowadays, in simple models as we have, simple problems, you can really get into enormous amounts of propositional variables in your representation, and you will still get efficient answers. So, practicalities, Davis-Putnam algorithm determines if a propositional logic sentence in closed normal form is satisfiable or unsatisfiable. If you find a model, it's satisfiable. If you don't find a model, it's unsatisfiable. It's basically a search procedure where each action is a choice of a truth value in a partial assignment. And basically the trick that is used is that you try to determine as early as possible if you have any contradictions, and the unit clause choice is one of them, because you know exactly the value of this proposition that you determine using the unit clause rule. We have a relatively simple heuristics on choosing the value if you have only one way of using the symbol, so not negated. For example, if you only use it in a positive way without negation, then it's a way of using it. And then choosing the right clause to work on next, the right symbol next is the other trick. So these are the 3 important tricks. So this I've already explained. So if you look later, this is the full implementation of the algorithm in pseudocode as it is in the book of AI, a Modern Application by Russell and Novick. So let's try, I don't know whether you brought a piece of paper or not, but let's see whether we can run such a problem given the Davis-Putnam algorithm. Because this is something you have to do in an exam. So I will then probably give you instructions. If you have a random choice, do it alphabetically. And if you have a random choice, so no unit rule, for example, then start with plus, a positive assignment, like they did with the negative example in the example I just gave. Let's start with the negative one. So basically, what do we have to do? We have to start with a partial assignment and then simplify our set. And we want to use the Mons heuristics. So not alphabetically, but Mons heuristics. So, anybody, what should I do to start with? Yes?
Using Mons heuristic, if you choose B, you create the most unit clause.
that is a good argument. It's not exactly the Mom's heuristics. So what he said was if you use P, you start out with P, then you create the most unit clauses, and that is sort of one step ahead of the Mom's heuristic is more simple. It just counts what are the minimal length clauses. We've got two of them, namely P R not R and P R Q. And which is the symbol that occurs most often in this clause, and that's P. So you're right in your argument. You're right in the result. The argument of the Mom's heuristic is even simpler. It's really simply counting the numbers. So that's something you can do in a linear one walk through the clause set. So you start with P, and now let's do it like they did in the example with the tree that I showed you. Let's decide P to be false. Yeah, P is false. So what is the clause set that we now get? So the first clause, P or not R, gets not R. Yeah. The second one gets not Q. The third one disappears. The fourth one disappears. Yeah, so this is all we've left. Unit clause. So it doesn't matter on which one we start. R is false. Q is false. Done. Yeah. So, of course, in the exam I will try to be a bit more difficult. Yeah. Yes. 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 It's a very good point. What Davis-Putnam does is it tries to find one model as quickly as possible. It doesn't say that it gives you all the models. Of course, if you don't stop once you found a model, it will eventually give you all the models. But it doesn't say that this is the most efficient way, and in the worst, that this is the most efficient algorithm for it. This algorithm is really geared for find one solution as quickly as possible. So I don't know what happened to this example. I had in mind that it was more difficult than this. But of course, the thing you need to understand and know is that in case you are not that lucky and find the solution immediately, you have to do this backtracking, and you have to understand this backtracking. And in the exercises tomorrow, there are examples that are sort of smaller even, but a bit more complicated. Yeah? And the way they are formulated, I think, also are that you don't necessarily start with the Mom's heuristics, which usually helps you to find a proof model very quickly. But you've seen that this is a sort of trivial exercise once you do the right heuristics, and that helps you. And just to give you an idea of what we are talking about here in terms of improvement, the difference between DPLL and the naive search, if you have 50 variables, which is not that much, but then the naive thing is, 6, 9, 12, 15, 10 to the power of 15, in the order 10 to the power of 15. So that already takes a long time to search for. And basically the reduction by Davis-Putnam, which has a worst case complexity, we're talking worst case complexity here, is 5 orders of magnitude better. Yeah? So you know exactly that that you're really, really faster if you use this more intelligent, I would say, implementation. And nowadays, reliably, hundreds and thousands, and in some specific cases, up to millions of variables can now be used. And this is exactly what for example, my field of research is, that how can we in automated reasoning, how can we find algorithms that solve these problems efficiently? Well, the nice thing is that we have now come up with a solution that makes reasoning more efficient, that can be applied on any problems that are translated into this formalism. And you run Davis-Putnam, and it will help you solve the problem. If you would implement this naively, the same sort of problem into a native Python program, for example, you would probably have a lot of efficiency to implement in your algorithm before you would be able to even solve problems that are half as large as this was. So the efficiency that we get out of understanding the logical mechanisms really help us make problem solving more efficient. End of preach. So the summary, for the practical perspective, Davis-Putnam, Loveland, and Lodgman determine satisfiability of formulas in closed normal form. Remember that if you want to use this for different logical purposes, so if you want to check, for example, for validity or for entailment in this case, you need to make a transformation from one problem to another. And in this case, instead of in order to show that a formula R follows from a knowledge base, you have to negate R, add it to the knowledge base, and show that the whole thing is unsatisfiability. So it's proof by refutation. So you suppose that your formula is false, and if you show that it's unsatisfiable, then you can conclude that the formula has to be true, given your knowledge base. So that's the practicalities that you need for running this, also for the knowledge bot. And the algorithm is, the procedure around the algorithm is, in order to show entailment of R with respect to the knowledge base, you translate the knowledge base into closed normal form. Then you translate the negation of the formula into closed normal form. You add the two things together. Then you apply Davis-Putnam until you find a model. And then you know it's satisfiable. Or you search exhaustively so that it's unsatisfiable. And if it's satisfiable, then you return A is not entailed, and otherwise you return A is entailed. That's the basic procedure of using this logical reasoning for entailment. So it's essential that you understand that for the exam. This is something you need to sort of work with in practice. Not very deep, not very complicated, but some simple examples you should be able to work with. So where we get into trouble here, when we want to apply this on the Schnatzen example, for example, is when we want to combine information about, yes, we have a jack and the queen has already been played, it's known where the queen is, and we want to play a cheap card, but not one, we want a risky strategy, whatever. So these qualitative statements, that's easy to take into account. But if we now want to also include information about the points that have already been played, so if my opponent has played fewer than 33 points and I have already 65, then I want to do something. So then we get out of the realm of qualitative statements into quantified statements, and basically what these things are is you're getting into some logic, some mathematical theories. So and basically there is an extension of propositional logic and propositional reasoning, which is called satisfiability modular theory, where the theory bit is a statement that can be interpreted to be true or false according to some other logic, some other formalism, such as the arithmetic logic that I've talked about on Monday. So basically, that's the picture that we've just seen. You have in Boolean satisfiability, so in propositional logic as we had it, you have as input possible variables to which you can give a value true or false, and then it determines the value of a formula, of a complex formula. But now we can have the same thing, but now where we don't have the propositions as simple statements, just as sort of atomic propositions, but where the propositions can be can come from some kind of mathematical theory. And the only requirement that we have is that we can interpret the theory in the same way as a true or false. So we need a theory that has certain properties. The question remains the same. So is there now an assignment to the variable such that the formula itself evaluates to true? And we can use all the operators of propositional logic as we've done before. So that's a recent addition to the SAT-solving problem. Recent, maybe the last decades, a couple of decades. And it simply extends classical SAT-solving by extensions of a theory that is decidable. So this is very useful in different kinds of circuit verification, software modeling. It is also useful in Schnapsen. It's not really something that I expect you to now go into depth with, but it's something, and also nothing I will sort of check in the exam. But it's something that can become very useful if you really want to model knowledge about the game, where the sort of the points you have already achieved and the points your opponent has really plays a role. So that's why I wanted to mention it. It's also mentioned in the worksheet, so something you can play around with, but we don't get into the theory here. The only thing you need to be aware of is that a theory such as equality of real numbers of arithmetic, if you use this as your theory, then you are allowed to write these kind of complex statements. If x1 is the same as x2, then two functions will be the same. And that's very powerful, of course, if you can combine this now with conjunctions or disjunctive reasoning or negation and so forth. So there is the property that you need that your sub-language that you talk about numbers, for example, and equality, it needs to be decidable. So there needs to be another algorithm, so it's a separate algorithm, one that is not within the Davis-Putnam framework, and we won't bother about this algorithm now. But we need an effective procedure to check if a formula is a member of that theory or not. And then you can use the elements from the core theory, so the classical propositional logic, and, for example, the integers theory. So you can use all the numerals as constants in the language. You can use the functions, the classical ones, the language that I was talking about. Similar, some comparators, equal, smaller than, and so forth. So I just wanted to mention this here as an extension of propositional logic that can be really useful and handy for those of you who want to get a bit more into depth of modeling of properties of the Schnapsen. So I think for most of you it will be interesting enough to look more on the qualitative side, but I'd be really interested in also see whether, taking into account the state of the state, so the state of the game, state not in the implementation sense, but in the, so how much am I in advance? Am I really about to win the game? Can you define what winning a game means in terms of the points that you have already achieved versus the points that your opponent has achieved in a declarative way? And this would be a formalism that's really helpful for that. And that's why we provide also a tool that can do this reasoning for a very specific theory as it's described in the worksheet. So play around with this, but don't lose too much time, particularly not as a preparation for the exam. So I have been really now hammering on this algorithm of Davis-Putnam, and last year we introduced two algorithms in the same sort of depth, and that felt heavy for some people, and sort of it doesn't really make that much sense. So I think it's really good that you understand one algorithm in depth and that you can sort of train it a little bit and that you understand it and that you also see the ins and outs a bit. So I choose the one that is also implemented in the algorithm. And so if you look at the code of the code base then and you look at kb.py, then there this algorithm is implemented. But I still think it's important that you're aware of the fact that this is not the only way of doing reasoning in these languages. And I've already quickly mentioned that there are other ways of doing this, namely this rewriting of the symbol. So it's a symbol Monjing that is really probably the more popular way of doing reasoning, in particular in more expressive languages. Because if you think of first-order logic that we've discussed yesterday and on Monday, remember that we can have large domains, infinite domains in the first place, and even worse, that we can have recursion in the definition of functions. So if you have think of defining humans for being people whose parents have been humans. So there's a sort of cyclic definition, and if you want to apply this in an exhaustive way, you have you get into an infinite cycle, basically. I have my, if I want to check whether I'm a human, I have to check an infinite cycle whether all my parents and my parents' parents and so forth have been humans. And basically that means that this way of looking at reasoning as model checking and model counting and model evaluation simply doesn't work, because we might deal with infinite models and done, over. Yeah? So we need something else. And first order logic and all the more expressive logics such as modal logic or description logics, which are the basis of the language OWL, for example, that some of you have seen, they don't do this model search reasoning anymore, but they do rule-based reasoning, manipulation of symbols in order to come from one part of the knowledge base to other facts that are valid or that are entailed by the knowledge base. So let me quickly get the general ideas of this out without getting into too much detail. What you basically have is an inference rule that says if I have a certain premise, so some of the things are part of my knowledge base, then I can safely add more information because it's logically entailed, so it's true information, but it helps me to maybe find the formula that I'm looking for. So it's often written in different ways. So you could write you can derive B from A. If you have alpha implies beta and alpha, then you can derive beta. So that's a very famous one. It's the inference rule of modus ponens that you all should have seen before. I think I should switch that off. Otherwise, you see who's online in whole of Europe. So there are different ways of writing this down, but the message is always the same. So whenever I have a physical form, formulas in some physical form, then I can simply rewrite the formula or add additional formulas. In some calculi, it is simply adding information, so it's a monotonous action. In some cases, you have to delete formulas, but it's always symbol manipulation. And here are some classical rules of propositional logic. So you have the modus ponens that we had on the other slide already. If you have alpha implies beta in the knowledge base and you have alpha in the knowledge base, then of course you can add beta. So that's a sort of a no-brainer in a way, and that's how they should be. Because of course, if I know that A implies B and I know A, then I also know that B has to be true. But it's a step to now transfer this to a reasoning algorithm, which says whenever I encounter this as a string, more or less, as symbols in my knowledge base, in my implementation, I can also add this new information. So if I have a formula such as A and B, I always can add one of those two to the knowledge base. And I can also use all the logical equivalences that I showed on Monday for rewriting. So if I have the formula alpha is equivalent to beta, we know that from semantically, this is equivalent to having the implication in the one direction, the implication in the other direction. So I can use this information about the logical entailment, the validity of the semantic equivalence of these two formula to simply rewrite my formula. These were these rules, and we have already used some of them for the CNF transformation. And you can also use it for reasoning. So basically, when you have a formula such as the one coming from the Wampus world, where we want to show that there is no pit in P11 and a breeze in 11, only if there is a pit in one of these two, P12 and so forth. So we have these three formula. We want to prove that P12 has no pit. Then all we have to do is to take these formulae and sort of shuffle them around, create new ones, add them to the knowledge base, because we know that it's a sound extension of my knowledge base, and try to find the one that I'm looking for. So basically, I wanted to check that there is no pit in 1,2. So this is what I want to show somehow, and this is what I can start with. So you have biconditional elimination that you can apply with some rule here. It's that rule. We have an equivalent, so we can replace it by the implication in both directions. We can eliminate the end, so we can only take one of the two conjuncts. We can contrapose, so that's a rule that works on the implication. If A implies B, then not B implies not A. That's the rule. Then we can apply modus ponens, and then we can apply Morgan's rule. And then basically we can do end elimination again in order to show that not P21 is, sorry, the other one, this one, that not P12 is entailed by my knowledge base just by symbol manipulation. And this is exactly what we had to show. Yes?
So this is basically doing algorithm, using an algorithm to do natural deduction.
Yeah, natural deduction has a different rule calculus. It's a different set of rules, but in a way,
a lot of it is
yeah, it's the same idea. So this is how the logicians sort of started to deal with notions of entailment. That they sort of, how would a human transform this information to this information? So how would you argue? And natural deduction tries it in a more sort of human kind of way. And the most extreme way of doing it is resolution calculus, which I will briefly mention in a minute. But the idea is that you, again, you can apply some search methodology, because in a way, if we start out with this set of formula up here, we have no idea with which rule to start. So it's nice and easy when I tell you which one to use, but you could have used all the 15 others first and seen it doesn't work, or it does work, or it doesn't get me anywhere. So we have another search problem. Which rule to apply on which part of the formula? And again, you can write down the whole thing as a search procedure, try to find the most efficient way to get from the original formula to the one that you want to prove, and so forth. Yeah? The one property of these rules I used was monotonicity, that whenever I add a formula, it's still true. So adding a formula that was entailed to the knowledge base doesn't change the semantics. So that's an important property of logics. There are logics where this doesn't hold, so then you really get into trouble with your reasoning algorithms. And try at home whether you can find, it's a good exercise, whether you can check whether this formula, F1, implies this one, and or both, whatever. So that's sort of just to make sure that you understand the basic idea of this rewriting algorithms. Again, when I said it's a search problem, you can always use, not always, but in many cases you can have two directions. You can start from the formula that you want to prove, that would be goal-direct, goal-driven, or you can start from the knowledge base and produce as many things as you could. So these rewrite rules, they can always also be used in the other direction in propositional logic. So it's important to make the choice, do I do a data-driven, a forward-chaining proof, or a backward-driven proof? So this is there really, if we do research on reasoning on the web, there is, of course, it's impossible to materialize, as it's called, to make all the information that's on the web of data making it explicit because there's far too much. So you can't apply this data-driven approach that I've just used in the example. You have to sort of try to, how can we show from a goal that it really is true? So the last part, very briefly, so that you have seen the word, I'm not sure whether this was covered in logic and sets. Resolution should be, I don't know. So resolution is basically the most extreme of all these rule calculi because it applies only one rule. So it avoids the basic principle. It has some other examples such as unit resolution, but in principle it uses one rule. It works only on clause normal forms, so that helps already because you don't have all these other operators. But after that, it only operates on clauses. It only does one thing, and that is checking whether in the clause there is a formula that occurs both non-negated and negated. So we have B here, not B here. We can delete both B and not B and create a new clause, A or B. That's all it does. It's a very, very, very brute force, simple algorithm, but it works astonishingly well, particularly for first-order logic, because there are some extensions to first-order logic that make this work. And it's it's a complete algorithm on its own for formulas in closed normal form, and it helps you decide on satisfiability of a propositional logic formula. Yeah? So only applying this one rule on clause sets helps you already to decide satisfiability. The same thing, the same principle as we just had with our Davis-Putnam algorithm applies here as well. So in order to show entailment, you have to convert the knowledge base plus the negation into closed normal form, and then you apply this resolution rule, this one rule, apply as long as you can exhaustively. And if you find a contradiction, you know that the thing has been unsatisfiable, and if you don't find a contradiction, you know that it has been satisfiable. If you find a contradiction, you know that there is no model. If you don't find a contradiction, you do not find a model. So you don't know what the solution to your problem would be. You simply know that there is one. So it's a very different approach as opposed to Davis-Putnam, Loveland, and Lodgeman. Yeah? So here's a picture of the algorithm, pseudocode of the algorithm. Very simple. You do closed normal form, and then you apply the resolution as long as you find what's called the empty clause, which is a contradiction. Simple, just have a look at it. And then there are some extensions when you have more complicated forms of clauses, but those are sort of the details that I don't want to bother you with. But if you're interested, just look at them. It makes sense to have some generalizations to make it a little bit more efficient. And then the last thing is that, again, resolution can be seen as a search problem. Which clauses you want to apply resolution to? Very similar to the choices that you have to make in Davis-Putnam. Which clauses do you want to, which properties do you want to satisfy true or false? The same you do in propositional logic, the same you do in resolution, choosing the fastest path from one combination of clauses in a resolution step to a contradiction that you can find. And that basically concludes my presentation today. Tomorrow we get into uncertainty and vagueness, two different concepts. And I hope you get going with the theory, but also particularly with the agents. Happy programming.